Now let's talk about an algebraic approach. How can I use the two formulas? Not the graphs, not an inspection by eyeball, but how can I use the two formulas to determine the x and the y coordinates of the point of intersection of these two lines? If both of these equations have to be satisfied, if the x and the y in one of these equations have to be the same thing as the x and y we get in the other equation, then what do you think is a strategy that we can use to make some progress toward getting these two equations down to a single solution? We're going to talk about two different methods. One we're going to spend some time on today, one we're going to spend more time on in our next class, and maybe naming the two methods will give you a clue as to what the first steps of those methods might be. The method we're going to talk about today is called the method of substitution. And the method we'll talk about in our next class is a method called elimination. And before we talk about the specifics of either of these two methods, let me tell you a little bit about what the goal is of each of these two. The goal for any solution method for a system of two equations, the goal is to reduce from two variables to one variable. Because we're starting with a couple of equations that each have an x and a y in them. And so we don't know how to get a number solution out of that. But if we can reduce from two variables into one variable, then we should get an equation that we can solve for that remaining variable and find a number value for that remaining variable. And these two methods are each going to be methods that are going to help us to do that. Go from equations that have both x and y in them down to a single equation that just has a single variable that then we can use all the techniques of solving equations that we know up to this point in the course to solve. So that's how we want to get there. So what do you think the method that we're going to talk about today, substitution, what do you think that that's going to tell us to do with these two equations? So the goal of substitution is to substitute. And the reason that it works is that each of these equations is telling me something about one of these two lines. The first equation is telling me that all the points on the red line have their x's and y's related by the equation y equals x plus 4. All the points on the blue line have their x and y coordinates related together by this equation. So if I'm looking for a point that belongs to both lines, then that must be a point, this point right here. At this point, one way of looking at it, at this point, y is equal, on the one hand, it's equal to x plus 4, but on the other hand, it's equal to x plus 4 because it's on the red line, but it's also equal to negative 7/3 x minus 6 because that point lies on the blue line. So y is equal to x plus 4 on the one hand, but it's also equal to negative 7/3 x minus 6 on the other hand. So what that tells me I can do is it tells me I can take the expression x plus 4, for example, and anywhere else that I see y in this entire problem, I can replace that y with x plus 4 when we assume that this point of intersection is a part of the red line, right? It's a point on the red line. And so what the method of substitution looks like is it looks like taking that x plus 4 from one equation and substituting it, just dropping it in to the other equation in place of the y. If I do that, what I end up with, x plus 4 equals negative 7/3 x minus 6, I end up with a single equation now, which is great, that's some progress. A single equation that, even more importantly, only has a single variable in it. My y's are gone, and I have an equation that only has x's in it. And once my equation only has x's in it, now I can solve that equation and get a number for x, which is ultimately what we're looking for. So that's what substitution does, is it takes that identity of one of our variables that's told to us by one equation, and it just drops it into the second equation in place of y, in this example, and thereby eliminates all the y's and gives me an equation that I can then solve for x. So let's use this equation, x plus 4 equals negative 7/3 x minus 6. Let's solve it for x. I'm going to choose to do that, again, by clearing denominators. if I multiply by 3 on both sides, then I will have the effect of clearing the denominator on this negative 7/3. That's going to turn it into negative 7 in particular. And then when I multiply all the other coefficients, 6 will become 18, x will become 3x, 4 will become 12. There we go. Then I need to get all my x's to one side. I'm going to do that by adding 7x to both sides. That will get all my x's to the left. I'm going to want to subtract, let's say, 12 from both sides. So let me do that part 2. I'm kind of compactifying a couple of steps here. I'm going to end up on the left side with 10x. On the right-hand side, I'm going to end up with, yeah, I screwed up again, minus 18. Yep, I did the same mistake that I made before. Sorry about that. When I copied down this equation, that turned into the wrong sign. Thank you. And so negative 18 minus 12, negative 30. And then finish by dividing both sides by 10. Negative 30 divided by 10 gives me negative 3. And that was the x-coordinate that we verified using the graphical technique as the x-coordinate of this intersection point. But the thing about the algebraic method is that we can't stop when we just have one of the variables solved for. We need to find the solution that also includes the y-coordinate that matches with that x. So what do you think? Now that I know that x is negative 3, how do I find out what y is supposed to be? Plug in negative 3 for x where? Yeah, well, so I have 2 equations to choose from. Which should I plug it into? Yeah, it doesn't matter. That's the other great thing about solving a system of equations, is it gives us, ultimately in the end, 2 different equations that I can choose to use to translate my x into my y. If the x that I found was correct, then either of these 2 equations is going to have to give me the same y. And so it should not matter which of these 2 that I choose. So I'm going to choose the one that doesn't have fractions in it, because that always seems like a good decision. So if we do that, we'll just plug that negative 3 back into the first equation, y equals x plus 4. And when x is negative 3, that gives me y equals 1. And again, make sure that your solutions to these problems do include both the value for x and the value for y. But this now is an illustration of the method of substitution that lets us use algebra to find the solution of a system of 2 equations. All it required us to do was to take one of the equations in which one of the variables has already been solved for. So that was the nice thing about this example, is that this first equation already had y by itself on one side. Y is equal to x plus 4. And that's what allowed us to take that x plus 4 and just drop it right into the second equation where the y appeared, and thereby eliminate the y's and give us an equation we can solve for x. We do the algebra to do that solving, and it gives us x equals negative 3. Then we just have to plug that x back into either, it shouldn't matter which one, of the original equations to then also find my value for y.